Howdy, welcome to Elementary Statistics. I am Lance Curtis. This is the lecture for Section 8.1, Basics of Hypothesis Testing. Here in this lecture, we're going to cover the basics of hypothesis testing. We'll start by introducing the concepts of the null and alternative hypotheses. Then we'll get into talking about confidence levels, test statistics, p-values, critical values. We'll talk about how to share the conclusions we make from hypothesis tests, as well as type 1 and type 2 errors, ways in which we can minimize those errors, and then conclude with a brief look at the power of a hypothesis test. Let's dive in. So, this section presents the individual components for a hypothesis test. When it comes to hypothesis testing, we need to know and understand a few things. First, we need to know how to identify the null hypothesis and the alternative hypothesis from a given claim, and how to express each of these in symbolic form. We need to know how to calculate the value of the test statistic provided a claim and sample data. We need to know how to choose sampling distribution that is relevant. We need to know how to identify the p-value and the critical value. We need to know how to state the conclusion about a claim in simple, non-technical language. So, to get started, let's talk about what is it that we're actually testing with hypothesis testing. What is a hypothesis? A hypothesis is simply a claim or statement about a property of a population. So we're looking at a population parameter, and we're making a claim about the value of that population parameter. The hypothesis test is then a procedure for testing the claim we make about a property of a population. This is all part of what we call inferential statistics, where we're taking a sample and we're using characteristics of that sample to infer or make conclusions about the characteristics of a population. When it comes to hypothesis testing, we only look at two types of hypotheses. So the first is what we call the null hypothesis, and the second is the alternative hypothesis. Now, every hypothesis test will contain both a null hypothesis and an alternative hypothesis. So let's take a look at each of these types of hypotheses in more detail. First, let's look at the null hypothesis. By definition, the null hypothesis is a statement that the value of a population parameter is equal to some claimed value. So equality, by definition, belongs with the null hypothesis. We typically denote the null hypothesis with a capital letter H and a subscript 0. This can be read either as H sub 0 or H0 or H naught. I typically use the reference H naught when referring to the null hypothesis. But you can see each of those denotations just as frequently as the other. I just simply prefer to use H naught. Now, we're going to test the null hypothesis directly in the sense that we assume that it's true in our testing procedure. And then we're going to reach one of two conclusions. First, we're going to reject H naught. This is one of the conclusions that we could reach. If we reject H naught, we therefore, by definition, accept the alternative hypothesis. Second, we could fail to reject H naught, and therefore fail to accept the alternative hypothesis. Now, as I said before, by definition, the symbolic form of the null hypothesis will always take an equal sign. So it's when you're working out with your problems and you're asked to find out what the null hypothesis is, you need to understand that it's always going to take the equal sign. Let's look now at the alternative hypothesis. This is a statement that the population parameter has a value that somehow differs from the null hypothesis. We're going to denote the alternative hypothesis with one of two symbols. We either use a capital letter H with a subscript 1, or we use a capital letter H with a subscript A. Either one of these denotations is used, and one can be just as common as the other. I've actually seen them both with equal frequency, so they're actually pretty much interchangeable. So when you see one of these, just think that this is a symbol for the alternative hypothesis. Now, because the alternative hypothesis, by definition, differs from the null hypothesis, hence the name alternative, the symbolic form of the alternative hypothesis is going to use an alternative inequality symbol. So whereas the null hypothesis always takes an equal sign, the alternative hypothesis will always take less than, greater than, or not equal to sign. Now, if you want to support a claim with hypothesis testing, the best way to do that is to state your claim so that it becomes the alternative hypothesis. Let's look at some examples to illustrate. Suppose that we have 100 babies born to 100 couples that are treated with an XORT method of gender selection that is claimed to increase the likelihood of having a girl. And then from this sample of 100 babies, we find that 58 of them are girls. Now, what are the null and alternative hypotheses that test the claim that with the XORT method, the proportion of girls is greater than the 50% that occurs without any treatment? Well, first, let's write the null hypothesis. So the proportion of girls is going to be greater than 50%. This is the claim that's made. But by definition, the null hypothesis always takes an equal sign. So we're going to put the equal sign in because by definition, the null hypothesis always takes the equal sign. The 50% value comes from the claim that the proportion of girls is greater than 50%. So from the problem statement, we get the value that's being claimed, and that goes in to form our null hypothesis. The alternative hypothesis will then have an inequality sign that's different from an equal sign. So we're not going to use the equal sign with the alternative because the equal sign belongs with the null hypothesis. The inequality sign that we use comes from the claim itself. Look at the claim in the problem statement. The proportion of girls is greater than 50%. So this then becomes our alternative hypothesis. The proportion of girls, which is P, is greater than 0.50. The proportion of girls is greater than 50%. This then is our alternative hypothesis. Let's test what we've learned about null and alternative hypotheses. So for each of the example claims that I'm going to show you, express the original claim in symbolic form, and then identify the null and alternative hypotheses. Let's look at an example. The claim is that the mean income for entry-level engineers is more than $35,500. A recent survey of 240 entry-level engineers showed a mean of $37,475. So first, what is the original claim in symbolic form? The claim is that the mean income is more than $35,500. So we're going to write that as the mean, which is mu for the population, is greater than $35,500. Here's our original claim in symbolic form. Now we need to identify the null and alternative hypotheses. The null hypothesis will then be mu equals 35,500. Remember, equality by definition belongs with the null hypothesis. So I just take that value from the claim and set it equal to my population parameter. The alternative hypothesis will then reflect the claim. Mu is greater than 35,500. And that's really all there is to it. Typically, for most of the problems that you work, you will see that the alternative hypothesis represents the claim. You just rip it straight off. Just take it right there. The null hypothesis is going to take an equal sign. The alternative hypothesis will take whatever the claim is. Let's look at another example. Here we have a claim that 20% of adults smoke. A recent Gallup survey of 1,016 randomly selected adults showed that 21% of respondents smoke. What is the original claim in symbolic form? Yes, I'm pausing so you come up with a response. So, producer response. What is the claim in symbolic form? The claim is that 20% of adults smoke. So this is a proportion. So we're going to say that P equals 0.2. The proportion of people who smoke in the population is 20%. Now, the null hypothesis will always take an equal sign. So we write that as the proportion of the population equals 20%. But wait, this is exactly what we had claimed. I thought that the alternative hypothesis always represents our claim. Usually it does, but that's not always the case. And here's a case where it doesn't. We can't actually say that P equals 0.2 is our alternative hypothesis, because by definition, equals always goes with the null hypothesis. So we have to set P equals 0.2 as our null hypothesis. What then do we write for the alternative hypothesis? Well, the alternative hypothesis is an alternative to the null, and in this case, we're going to take the complement of equals, which is not equal to. So when the claim is that our population parameter equals a claimed value, then our alternative hypothesis will take the not equal sign. Notice the value that's claimed is the same value all throughout, the 0.2. The only thing that's different is the actual inequality sign that we use for our alternative hypothesis. Again, we can't use equals with H1 because H0 uses it by definition. So then we have to take the complement of equals to provide the alternative, and that's where we get the not equal from. Let's look at one more claim. The mean pulse rate in beats per minute of adult females is 76 or lower. For a random sample of 40 adult females, the mean pulse rate is 77.5 beats per minute. So, the original claim in symbolic form is going to be that mu is less than or equal to 76. That's what we claim, that the mean pulse rate is 76 or lower. So, writing that symbolically, we have mu is less than or equal to 76. The null hypothesis then. What will the null hypothesis be? I hope you said that the null hypothesis is going to be mu equals 76. That's what it is. Equality always goes with the null hypothesis. The alternative hypothesis then comes from our claim. Now, notice that we're actually swapping the inequality sign to make our alternative hypothesis. This is because our claim has a sense of equality to it. The claim is that mu is less than or equal to 76. Well, the or equal to portion belongs with the alternative hypothesis. So since we took that out and put it with the null hypothesis, we have to switch the inequality sign on the alternative hypothesis. Because again, we're looking for complementation. So here the complement we're looking for is greater than 76 because that's the complement to less than or equal to 76. Let's talk for a moment about significance levels. So once we have the null and alternative hypotheses, the next step in our hypothesis test is to select a significance level. Typically for the problems that you work, you're going to have a significance level given to you. However, in the real world, when you're performing hypothesis testing with real-world problems, you'll have to select the significance level yourself. Now, the significance level is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. In other words, we're making the mistake of a type 1 error. We're rejecting the null hypothesis when it is true. We'll get more into type 1 and also type 2 errors later in this lecture. For right now, let's actually focus on the part of the definition for significance level is that it falls into the critical region when the null hypothesis is actually true. We're assuming with the hypothesis test that the null hypothesis is true, but we don't want to reject the null hypothesis when it is actually true. We want to fail to reject the null hypothesis when it is actually true. So there are different levels of significance that we can attach to our hypothesis test that correspond with the probability of actually making a proper conclusion from our test. First, we're going to denote the significance level with the lowercase Greek letter alpha. This is the same alpha that we've seen previously in chapter 7. So there's no difference here. It's the same alpha. Now, what we select for significance level is often determined by the seriousness of a type 1 error. If the error is very serious, then yes, we're going to want to make alpha smaller, as small as we can be. But if it's not as serious, then we can tolerate a higher level of alpha. So the more severe the consequences of rejecting a true H0, the smaller alpha should be. Typically, you have some common choices for alpha, such as 10%, 5%, and 1%, with 5% by far being the most common choice. Many real-world applications simply take a 5% alpha as a default value without considering the relationship that the alpha has with the type 1 error. Well, again, we'll talk more about type 1 and type 2 errors also later in the lecture, but you really want to select your alpha level based on the parameters of your situation and not just take a default value because that's what's always been used. Let's talk for a moment about the test statistic, because once we have the level of significance, now we're going to actually have something to compare with, and one of the things that we use for comparison is a test statistic. So the test statistic is simply a value used in making a decision about a null hypothesis. We use the test statistic in a comparison, as we'll see here shortly, and then based on the results of that comparison, we can make a conclusion from our hypothesis test. We're going to calculate the test statistic by converting the sample statistic we have into a score. Again, assuming that the null hypothesis is true. The logic that's used in deciding which of these test statistics we calculate is the same logic we saw for calculating confidence intervals from chapter 7. So, when we're dealing with proportions, we want to calculate a z-score. If we're dealing with a mean value, we're going to calculate either a z-score or a t-score. Again, the key question is, do you know what the population standard deviation is? If you don't know what the population standard deviation is, you're going to calculate a t-score. If you do know what the population standard deviation is, then you're going to calculate a z-score. Notice the z-score for a mean value is calculated differently from the way the z-score is calculated for the proportion. So there's definitely a difference there. For standard deviation of variance, we're going to use a chi-square distribution to calculate a chi-square scored, as you can see here in the table. So we have the same logic of selecting our appropriate distribution for hypothesis testing that we did for confidence intervals. Now, don't worry too much about having to know how to calculate the test statistic from each of these equations that you see here in the table. You'll be able to use StatCrunch to calculate test statistics for you, as we'll see here in a moment. First, let's relook at our example and apply what we've learned so far. Let's again consider the claim that the XORT method of gender selection increases the likelihood of having a baby girl. Now remember, for the 100 couples that gave birth, each gave birth to a child, 58 were girls and 42 were boys. So, from the chart on the previous slide, we're dealing with proportions, so our test statistic is what you see here. P hat is going to be the sample proportion. So this is the 58 out of 100 children that were born girls, or 58%. P is the probability of success. So, all things being equal, it's equally likely you could have a girl as well as a boy, so the probability of success is 50%. Q is the complement of P because it is the probability of failure. So we simply subtract our 50% from 100%, or take 0.5 if you have it in decimal point. If you have it in decimal form, take 0.5 away from 1, and we get the same 50% out as a value for Q. Now we have everything we need to calculate our z-score. So we substitute the values that we have into our equation. So 58% for P hat, 50% for P, 50% for Q. Our sample size N is 100. So we just punch this out on our calculator, and out comes 1.60. Again, it's not likely that you'll have to calculate any of these test statistics by hand, because if you have the actual data that you need, and most often you will, you can actually use StatCrunch to calculate this for you. Let's first look at how we use the actual test statistic. Once we have the test statistic calculated, we need to compare it with a standard so that we can make a conclusion that resolves our hypothesis test. We're going to need to know whether we reject H0 or fail to reject H0. And typically this is done by looking to see if our test statistic is inside the critical region or outside the critical region. Now, there's two different standards that we can use. We can either use a critical value or we can use a p-value. We just have to remember to make comparisons of like with like. So if we have a test statistic, we're going to compare that test statistic with a critical value, because test statistics and critical values are both horizontal values for our distribution. Now, whichever standard we use, it's going to depend on whether our alternative hypothesis reflects a critical region in the left tail, the right tail, or both tails of our distribution. So, if we have a left-tailed hypothesis test, that means our critical region is on the left. And we can tell this because our alternative hypothesis will use a less than sign for the symbolic notation. A right-tailed hypothesis test has a critical region on the right. Here we see our alternative hypothesis will use greater than sign for an inequality sign. Two-tailed hypothesis tests have a critical region on both sides of the distribution. Here we find our alternative hypothesis uses a not equal to sign. So, depending on the inequality sign used in our alternative hypothesis, we can tell right away what type of hypothesis test we have: left-tailed, right-tailed, or two-tailed. And this tells us the location of our critical region. finding this critical region is absolutely important because it lets us know whether we can reject the null hypothesis or fail to reject the null hypothesis. Now, we can do this the old school way, but StatCrunch makes finding test statistics really, really easy. So we can calculate this out by hand as we were doing just a moment ago, but it's much, much easier to use StatCrunch. So the great thing about this is that we don't have to learn any new menu commands. The same way that we use StatCrunch to set up our confidence intervals is going to be the same way that we use StatCrunch for hypothesis testing. The only difference is that when you get into your options window, you want to leave the default radio button selection on hypothesis test. Don't switch it over to confidence interval like we were doing previously in Chapter 7. You want to just leave it there with hypothesis test. You're going to have to fill in the values there for your null hypothesis and alternative hypothesis, but that's easy enough to do once you know how to make them. Put in the sample data up at the top like you always do, press compute, and out comes a results window where you see the test statistic listed there at the bottom. The test statistic will always be the next to last value listed in the results window table. So we see here that our test statistic, 0.4472, this is the test statistic that we have for the XSort gender selection method example that we were looking at previously. Let's look at another example for calculating the test statistic. Suppose the claim is that the mean income for entry-level engineers is more than $35,500. A recent survey of 240 entry-level engineers showed a mean of $37,475 and a sample standard deviation of 2,384. What then is the value of the test statistic? Well, first thing we need to do is look to our null and alternative hypotheses. Do you remember how to make the null and alternative hypotheses for this particular claim? We actually looked at this on an earlier slide. Do you remember what this was? What's the null hypothesis? Okay, now that you've given a response for the null hypothesis, I'd like you to give another response for the alternative hypothesis. What is the alternative hypothesis? Okay, well, I hope that you put this down. This is the null hypothesis and the alternative hypothesis for this particular example. The claim is that the mean is more than 35,500. So that's going to be our alternative hypothesis. The null hypothesis, by definition, always takes an equal sign. So we're going to write mu equals 35,500 for our null hypothesis, and mu is greater than 35,500 for our alternative hypothesis. Now that we have the null and alternative hypothesis, we're ready to calculate our test statistic. Go into StatCrunch and go to tstat one sample with summary. Why are we using tstat when calculating a hypothesis test for the mean? Remember, when we're looking at the mean value, the key question is, do you know what the population standard deviation is? Do we know what the population standard deviation is? No, we don't know what the population standard deviation is. There's no mention of it made in the problem, which means we have to assume it's not known. That means we're going to use a t-statistic. We're going to use a t-score as our test statistic. So we want to go into t-stats and not z-stats. When we get to our options window, we're going to put in the information that's required. Notice how we put in the sample statistics just as we normally would. So the sample mean, 37,475, sample standard deviation, 2,384. Our sample size is 240, so we'll stick that in here. We leave this radio button, this is the default. we leave this radio button alone, make sure it's for hypothesis testing, but we have to put in our claimed value, which is the 35,500, and then we have to select the proper inequality sign from this drop-down menu for our alternative hypothesis. So we make sure that that matches up, and then once we do that, we're all set to go. So we go in and put compute, and out comes the results that we get, and the test statistic is always the next to last value in the results window. So here we have our test statistic, 12.83. Now, if you wanted, you could take that equation that we saw earlier and compute this out by hand. You'll see you'll get the same thing. It's just much easier to do it in StatCrunch. It's also much easier to do it this way because now we've actually conducted the hypothesis test. So we actually have the information we need to conclude the hypothesis test, make our conclusions, and that's all she wrote. Alternatively, instead of using a t-statistic for making our decision, we can use a p-value. So let's talk about calculating p-values. P-value, which is a shortened way of saying probability value, is essentially the probability that the test statistic is at least as extreme as the one representing the sample data, with the assumption that the null hypothesis is true. What this basically comes out to be is, because it's a probability, this actually represents an area underneath the curve. Specifically, it's going to be the area of the tail bounded by the test statistic. So, if we have a left-tailed hypothesis test, the p-value will be the area to the left of the test statistic. If we have a right-tailed hypothesis test, the p-value will be the area to the right of the test statistic. If we have a two-tailed hypothesis test, the p-value will be the area under both tails of distribution. So you're going to have a test statistic on the right and the left, and it will be the area in each of the tails. For a symmetric distribution, such as the standard normal distribution or the student t-distribution, the value of the area in each of these tails will be identical. And therefore, the test statistic will simply have the same absolute value on each side. One will be positive and one will be negative. For the chi-square distribution, that's not true. The distribution is not centered about 0, and the distribution is skewed. So therefore, you're going to have two separate values for test statistics for a two-tailed test involving the chi-square distribution. And the area under each of these, bounded by each of these areas, may not necessarily be the same because the distribution is skewed. So, regardless of which type of hypothesis test you have, you're going to reject H0 if the p-value is less than the significance level. Again, typically this is a small value like 5%. If it's not less than the significance level, then you'll fail to reject H0. Only when the p-value is less than the significance level are you inside the region of rejection. And so only then will you reject H0. Otherwise, you're not in the rejection region, and therefore you fail to reject H0. Let's look at critical values, because if we don't use the p-values and compare it with the standard of our significance level, then the critical value becomes the standard by which we use for comparison with the test statistic. So the critical value is simply the boundary of the critical region in our distribution. Remember, the significance level alpha determines the size of the critical region. Because it determines the size of the critical region, it also determines what that boundary to the critical region is, and that boundary is the critical value. So if our test statistic lies inside the critical region, then we're inside the region of rejection, and we reject H0. If, however, our test statistic is outside the critical region, we're going to fail to reject H0. Let's go back to our XOR gender selection example to illustrate. From our alternative hypothesis, we know we have a right-tailed hypothesis test. This means our critical region is in the right tail of our distribution. Go back and look at the alternative and null hypotheses for this particular example. We had the proportion equals 50% for the null hypothesis, and the proportion is greater than 50% for the alternative hypothesis. We know we have a right-tailed hypothesis test because look at our alternative hypothesis. It's using the greater than sign. You can think of this like an arrowhead pointing in the direction where the critical region is. So here we have an arrowhead pointing to the right. So our critical region is on the right side of our distribution. We have a right-tailed hypothesis test. This means the critical region is in the right tail of our distribution. Now that we know this, we can use our p-value to complete our hypothesis test. First, we get our test statistic, which is 1.6. This borders an area under the curve to the right of 0.548. Now, we can get our test statistic using StatCrunch to use the hypothesis testing. But supposing we don't have any sample data, how then do we use the test statistic to get our p-value? Well, we'll simply use our calculator, our distribution calculator inside StatCrunch. We're looking at proportions. So for proportions, we want to use the standard normal distribution. We'll put in our test statistic. This is our horizontal value, so it goes to the left. We have a right tail distribution, so we want to select greater than or equal to from our inequality drop-down menu. Hit compute, and out comes the area under the curve, which is our p-value. This is the area bounded by the test statistic. We're now going to compare the p-value with the significance level. We weren't given a significance level when the problem statement was given to us, so let's just assume that the alpha level is 5%, which is a pretty safe assumption since this is commonly selected. Because our p-value of 0.0548 is greater than 0.05, the area bounded by our p-value is greater than the area bounded by our critical value. This means we are outside the rejection region, and therefore we fail to reject H0. If you look at this graphically, think of the p-value as the area under the curve bounded by our test statistic. We're going to compare that with the critical region area under the curve, which is equal to our significance level, alpha. Because the p-value area is greater than the critical region area, we can't fit the p-value area inside that critical region because it's too big. It can't fit in. It's bigger than that. Therefore, we can't be in the rejection region, and therefore we fail to reject H0. Alternatively, we can use the critical value to complete our hypothesis test. Let's see how this is done. So, with a significance level of 5%, this means we have a critical value of 1.645. Again, we've calculated this before in previous chapters, but if you want to go back into StatCrunch, use the calculator for the standard normal distribution, put in 5% for your area, and you see that the horizontal value that comes out, the critical value, is 1.645. Now we compare our test statistic with our critical value. So our test statistic is 1.6. We compare it with our critical value of 1.645. 1.6 is less than 1.645. Therefore, we are outside the critical region, and we therefore fail to reject H0. If you look at this graphically, here we have a right-tailed hypothesis test, the critical value forming the boundary of our critical region. So the left side of that critical region, shaded in red, underneath our distribution, there in the tail, on the right side, that value is z equals 1.64. Our test statistic is just to the left of that at z equals 1.6. Therefore, we are outside this critical region. Therefore, we are outside the rejection region. Therefore, we fail to reject H naught. Notice that no matter which way you go, no matter which comparison you're making, you get the same result. No matter which way you go. So it doesn't matter which way you go. Typically, the easiest way to do that is to just look at the p-value, because you put in your information to do the hypothesis test and stack crunch, and the p-value comes out in your results. And so you don't have to calculate a critical value to compare with the test statistic. You just compare the p-value with the significance level, which is typically given to you in the problem statement. So it's simply much easier to use the p-value, but it's good to know how to calculate it using the critical value as well. So, just as we got done talking about here, p-values appear in our results windows in Stack Crunch. There's a caveat to this, and that is that you can use this feature to find p-values only if you're given sample summary stats or sample data. You need either summary stats or the actual data itself in order to get to this results window in Stack Crunch, because these are inputs required in the options window. So you can't actually get the p-value using the hypothesis test method in Stack Crunch unless you have summary stats or sample data. If you have neither one of those, then you have to go back to your distribution calculator to get your p-value. Now, some of your homework problems do not give you any information for your respective sample, which means you have to use the correct distribution calculator to get the p-value to come out. And that's not really a problem. You just have to understand which distribution to use in which situation. Again, this follows the same logic that we had in Chapter 7 for constructing confidence intervals. So, for the example we've been looking at previously, where we're looking at proportions, we want to use a standard normal distribution. So we go to the normal calculator and we put in whatever significance level we have, which in this case was 5%. So alpha is 0.05. We put that in for our area and compute, and out comes our critical value that we can then use for testing with the test statistic. Alternatively, if we have we can actually get the p-value that comes out if we have okay, I misspoke here. So the test statistic bounds the area for the p-value. The critical value bounds the area for alpha. So if we have one of those, we can find the other for each of those pairs. Remember, p-values are areas under the curve. So we have to compare them with alpha, because alpha's significance level is also an area under the curve. The critical value is the horizontal axis value bounding the critical region. We compare that with the test statistic because it is the value that it's the value that bounds the area that makes up the p-value. So again, looking at the readout from our distribution calculator, critical values are on the horizontal axis. So they're going to be located to the left of the equal sign. Whereas p-values are areas, they're going to be values that you see on the right of the equal sign. Let's look at an example to illustrate. So the test statistic z equals 2.00 is obtained when testing the claim that p greater than 0.5. What is the p-value? Well, here's an example where we're not given any sort of summary statistics or sample data. So we can't use the hypothesis testing option in StatCrunch to calculate our test statistic or p-value. So how do we get the p-value? We have to use the distribution calculators. So here we want to actually use the normal distribution calculator. Why are we using the normal distribution calculator? Because we're talking about proportions. We then take the test statistic, and that's going to be the area that bounds the area that's representing the p-value. So here we have our normal calculator. We put 2.00 in. This is the horizontal value, our test statistic, and it's going to provide the boundary for the area under the curve that is the p-value. So we press compute, and out comes an area of 0.0228. This then is the p-value. Notice we have a right-tailed test. We use this to reflect this into our calculator in StatCrunch. Notice our test statistic goes on the left. The p-value then comes out on the right. So we have the area under the curve, that is the p-value, is bounded by the test statistic. Alternatively, we have a critical region that has an area equal to alpha, our significance level, and it's bounded by the critical value. So when we're making conclusions from our hypothesis test, we need to make a comparison. We're going to compare like with like. So we either compare horizontal values or we compare areas. If we compare areas, we're comparing the p-value with the alpha level. If we're comparing horizontal values, we're comparing the test statistic with the critical value. So what is the critical value if alpha equals 0.05? Well, that's easy enough. Just put that into your calculator in StatCrunch. We're using the normal distribution because, again, we're talking about proportions. The critical value is then going to be the horizontal axis value bounding the critical region, which is the area equal to alpha. So here we have a mean and a standard deviation, 0 and 1. This is our standard normal distribution. We put in the value for the area, 0.05. This is our critical region area, alpha, and then we press compute, and the critical value, which is the horizontal value, the value on the horizontal axis, 1.645, comes out. So our alpha level goes on the right. The critical value comes out on the left. So if we're using a p-value, we want to compare the p-value with the significance level alpha. If the p-value is less than or equal to alpha, we're inside the rejection region. The area that is the p-value can fit inside the area for the rejection region. Therefore, we reject H0. However, if the area for the p-value is larger than the area for the rejection region, then we're going to fail to reject H0. If we use a critical value, we're going to compare the test statistic with the critical value. So we're comparing again like with like, horizontal values with horizontal values, areas with areas. So if our test statistic resides inside the critical region, we're inside the rejection region, therefore we reject H0. If we're outside the rejection region, then we're going to fail to reject H0. So it's the same basic concept. You just have to remember to compare like with like. So the p-value method is where you're comparing areas. The critical value method is where you're comparing horizontal axis values. We're going to reject H0 when we're inside the critical region. We're going to fail to reject H0 when we're outside the critical region. This brings us to the point where we're ready to make a conclusion about our hypothesis test. Oftentimes, though, these statistical tests are performed for the benefit of those who are not familiar with the methodologies of statistics. And so, using the language of statistics is not going to really communicate anything to these people. So it's especially important, especially when you're talking with decision makers, to state the conclusions of your hypothesis test in language that they can understand. Now, the proper wording that's used differs slightly, but it's very significant. So, depending on whether you have a one-tailed, a two-tailed, or whether you reject or fail to reject H0. Typically, when you reject H0 in a one-tailed test, you're going to say there's sufficient evidence to warrant the claim. However, if you fail to reject H0 in a one-tailed test, you're going to say there is not sufficient evidence to warrant the claim. If you reject H0 in a two-tailed test, you will say the sample data support the claim. If you fail to reject H0 in a two-tailed test, you will say there is not sufficient evidence to support the claim. So looking back at the XSort gender selection method example that we've been looking at throughout this lecture, we can make the conclusion, since we failed to reject H0 in a one-tailed test, remember it's a right-tailed test, so that's a one-tailed test, we would say there's not sufficient evidence to warrant the claim that with the XSort method, the proportion of girls is greater than the 50% that occurs without treatment. This is very specific language, but it's also language that those who are not familiar with statistics can readily understand. Let's keep in mind some considerations when we're making conclusions about our hypothesis tests. You never want to conclude a hypothesis test with a statement of reject the null hypothesis or fail to reject the null hypothesis. Again, you want to use language that those who aren't familiar with the methods of statistics can understand. Now, there are some statistics textbooks and other resources online that use phrases like accept the null hypothesis. What they're trying to do is communicate the method of statistics to teach people those methods in a way that they can understand better. Admittedly, the two options that we're left with, we reject the null hypothesis or we fail to reject the null hypothesis, is counterintuitive to the way most people think. And so the idea of representing this as accepting the null hypothesis rather than fail to reject the null hypothesis makes more sense to some people. And so this is the way that some resources have been aligned to teach this material. However, we have to understand such statements really aren't correct. To say that we accept the null hypothesis means in essence that we're trying to prove it. But we're not trying to prove the null hypothesis. We actually have an assumption in our methodology that the null hypothesis is true. Furthermore, the alternative hypothesis is what reflects the claim that we're testing, not the null hypothesis itself. So there's really no accepting of the null hypothesis when the claim that we're being tested is in the alternative hypothesis. Fail to reject the null hypothesis is really the correct language that we need to use, because it says that the available evidence is not strong enough to warrant rejection of the null hypothesis, and with it acceptance of the alternative hypothesis and the claim that it reflects. So you want to be very careful about the language that you're using, and certainly you will have problems that you need to solve where you need to be very careful about that language that you select. Let's look at an example. Again, the mean income for entry-level engineers. So we have the claim, we have the sample data, they have the summary stats from the sample data, and so now we're asked to make a conclusion about the null hypothesis. Well, we run our hypothesis test and we get these results out in StatCrunch. So now what do we do to conclude our hypothesis testing? What conclusion can we make about the null hypothesis? Do we reject it or do we fail to reject it? Well, if we use the p-value, notice we have a p-value here that says less than 0.0001. When you see this, you can say that the p-value is essentially 0. And for all practical purposes, it is. So 0 is going to be less than our alpha level, which was 5%. So therefore, we're inside the rejection region, and we reject H0. Alternatively, if we use the test statistic 12.834, we're going to compare that with the critical value, which remember we got, that's the horizontal value that bounds the area for our alpha. So that's 1.645. So that's going to be less than our test statistic. So therefore the test statistic is inside the rejection region, and therefore we reject H0. Again, either method you use, you reach the same conclusion. How then should we state our conclusion in non-technical terms? Well, we have 4 options that are listed here. There is sufficient evidence to support the claim that the mean is more than 35,500. There is not sufficient evidence to support the claim that the mean is more than 35,500. There is not sufficient evidence to reject the claim that the mean income is more than 35,500. And there is sufficient evidence to reject the claim that the mean income is more than 35,500. If you compare each one of these answer options, you'll see that they're exactly the same, except for some slight difference in the wording towards the beginning. There either is or is not sufficient evidence, and you're either supporting or rejecting the claim. Which one do we want to use here? Well, we have a one-tailed test or a two-tailed test. We have a one-tailed test. Therefore, we're going to be looking at the answer options that talk about supporting the claim. If we had a two-tailed test, then we would look at the answer options that talk about rejecting the claim. So now we have to look at and say, which do we choose? Is there sufficient evidence or is there not sufficient evidence? And in this case, we're going to select that we rejected H0, therefore we have sufficient evidence. So, the correct answer is answer option A. There is sufficient evidence to support the claim. There is sufficient evidence because we rejected H0, and we're going to support the claim because we have a one-tailed test. Again, if we had a two-tailed test and we rejected H0, then we would pick answer option D. There is sufficient evidence to reject the claim. But here we're looking for supporting the claim because we have a one-tailed test. We rejected H0, therefore there is sufficient evidence. The correct answer option here is answer option A. Let's look at another example. We're forming conclusions with coin tosses. So a coin favors heads is our claim. We have a sample that shows 11 heads among 20 tosses. So we have 11 heads and 9 tails and 20 tosses. Now, what subjective conclusion can we make about the given claim? Well, here we're looking at proportions, and we're saying that the proportion is going to be greater than 50%. Because the coin favors heads. So the proportion of heads in our population is going to be greater than 50%. That's the claim, because it favors heads. However, we look at the sample and we see that, well, no, actually 11 out of 20 is really right around 50. So, yeah, there probably is evidence that we're going to use to support the actual claim itself. So here we're actually going to choose answer option C. There is not sufficient evidence to support the claim that the coin favors heads because there's not substantially more heads than tails. That makes sense when you consider that 11 out of the 20 coin tosses were heads. It's about 50%, and that's what we would expect from a coin that's actually fair. Let's look at another example forming conclusions involving the mean income for entry-level engineers that we've been looking at previously. What subjective conclusion can we make about the given claim? So again, we're not going to run through the whole hypothesis testing stuff. We're just looking at subjective conclusions. So from the sample, we see that the entry-level income is greater than what's actually claimed. So there does appear to be sufficient evidence to support the claim that the sample results are more than what's actually being claimed. So this is answer option A. Now, some may wonder, what is it that we're actually trying to do here? I mean, anyone can look at these numbers and see 37,475 is greater than 35,500. So why do we even need to run the hypothesis testing to begin with? Well, the purpose of a hypothesis testing is to make an inference about the population. Of course we know that 37,475, which we have in the sample, is greater than the claim value of 35,500. But what is the mean value of the population? Do we really know what that is without taking data from each and every member of the population? We don't want to do that. That's too time-consuming, too taxing, and not very likely to come because you're going to have some people that likely aren't going to want to share their income level with you. So we want to use the sample data to make an inference about the population data. And that's where the hypothesis test comes in. We're actually testing to see if what is in the sample can be transferred or inferred about the population. Let's talk now about type 1 and type 2 errors. I said we would come back to this. So let's talk more about type 1 and type 2. We've actually seen type 1 and type 2 errors before. Remember that a type 1 error is the mistake of rejecting the null hypothesis when it is actually true. The probability of committing a type 1 error is represented by alpha, which is the same alpha we've seen all along. It's the same alpha we saw in chapter 7 with confidence level. It's the same alpha we're seeing now in chapter 8 with significance level. It's the same, it's all the same alpha. The type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. So this is the probability of committing a type 2 error is represented with the Greek letter beta. So now let's actually translate all of this statistic ease for our gender selection example. Remember that our null alternative hypothesis are what we see here on the screen. So the proportion of girls is equal to 50% is the null hypothesis. The proportion of girls is greater than 50%. This is our claim. It's represented in the alternative hypothesis. So a type 1 error is rejecting a true H0. So if H0 is true, the proportion of girls born is 50%, the type 1 error would be concluding the probability of girls is greater than 50% when in fact it's not. It actually is 50%. The type 2 error, failing to reject a false H0. So that means that H0 is actually false. So the proportion of girls is not 50%. And the type 2 error would then be concluding that there isn't sufficient evidence to say the probability of having girls is greater than 50%, when in fact it is. In either case, we simply need to get more data. If you have a type 1 or a type 2 error, the way to minimize that is to get more data, as we'll see here shortly. First, let's look at an example. So going back to this mean income example we've been looking at, The claim is that the mean income for entry-level engineers is more than $35,500. Identify the type 1 error. Choose the correct answer below. So you have 4 answer options here, and it's a really good idea when you get these types of problems to look at the wording in each of the answer options. You're going to find that they're mostly the same, except for some key differences. So looking over these answer options that we see here, what are the key differences between them? If you look this over, you can see that the key differences in the wording of these answer options is at the beginning and at the end. The beginning can be that we reject the null hypothesis or we fail to reject the null hypothesis. And then at the ending of each statement, you're saying that the mean value is actually less than 35,500 or equal to 35,500. So now we have those key differences in play. Let's actually look to see where the type 1 error would be. First, let's review what a type 1 error actually is. So a type 1 error, remember, is where H0 is actually true, but we end up rejecting it. So what would make H0 true? We'll go back to your null and alternative hypothesis. Remember, the null hypothesis said that the population mean equals 35,500. So that means that if H0 is actually true, then the mean value is actually equal to 35,500. So right here we can eliminate answers A and B from being the correct answer, because these answer options say that the mean value is less than 35,500, the statement that's there at the end of each of those answer options. So H0 is true, that means mu equals 35,500, so it's got to be C or D. So, do we fail to reject the null hypothesis or do we reject the null hypothesis? Well, if H0 is actually true, then the mean value is equal to 35,500. But did we fail to reject the null hypothesis or reject the null hypothesis when we conducted our hypothesis test? We rejected the null hypothesis. Therefore, the correct answer is answer option D. In solving these types of problems, you have to be very careful looking at the wording of each of your answer options and then choose accordingly. The same process works when you're asked to find the type 2 error. So let's do that for the same example of mean income. Again, if you read through the answer options that you see, you'll notice that the key differences in the wording are we're either rejecting the null hypothesis or failing to reject the null hypothesis. And then we're saying the mean value is actually different than 35,500 or equal to 35,500. So what is a type 2 error? Remember, a type 2 error is where we fail to reject false H0. H0 actually is false. But what is H0? Again, go back to your null and alternative hypotheses that you constructed originally. So the null hypothesis is that mu equals 35,500. If H0 is actually false, that means the mean value is actually different from 35,500. So right off the bat, we're going to eliminate answer options C and D, because we're saying the mean value is actually different from 35,500. So it's going to be A or B. Now, did we reject or fail to reject the null hypothesis in this example? We rejected the null hypothesis, and therefore the correct answer is, we failed to reject the null hypothesis. Therefore, because the type 2 error is failing to reject a false hypothesis. So we're going to fail to reject the null hypothesis, even though it's actually H0 is actually false. So answer option B is the correct answer. obviously, these types of errors are things that we want to minimize. So there's different ways that we can actually control type 1 and type 2 errors. If we fix our sample size n so that it doesn't change, we can actually change the values of alpha and beta, but they're kind of inversely proportional to each other, as you can see here from the graphic at the bottom of the screen. So if we take these two distributions and we're fixing sample size, so the size of these distributions is not going to change, we can move these distributions together to the left. That will increase beta, but it will also decrease alpha. If we move the two distributions the other way, and we're moving them together because there is no change in sample size, then that means that the blue area gets smaller and the red area for the type 1 area gets bigger. So obviously we have to make a compromise there. If we have a fixed sample size, we're going to have to find a spot where we can live with the values of alpha and beta. Because no matter which way we go, if we increase one, that's going to decrease the other. Well, what happens if we don't have a fixed sample size? Let's say we actually fix alpha instead. Okay, so now that we're fixing alpha, okay, that means that our sample size can change, which means the size of our distributions can get bigger. The shape of our distributions can be altered slightly. So the increase in a sample size, if we keep alpha constant, that's going to cause a decrease in the value of beta. Because changing our sample size is going to move just one of those distributions and not both of them together. Conversely, if we fix beta, then an increase in sample size will cause a decrease in alpha. So how is it that we get a decrease in both alpha and beta? The answer is increase your sample size. You need to get more data. And that's why one of the major concerns in any statistical study is, have we obtained all the data we can get? Always get more data. If you have the ability to get more data, because this will minimize the probability of having a type 1 or a type 2 error. It will also provide a sample that's, generally speaking, all other things being equal, more characteristic of the population. So if we want to decrease both alpha and beta, we have to increase the sample size n. This leads us to what's called the power of a hypothesis test. The power of a hypothesis test is what statisticians basically call the probability 1 minus beta of rejecting a false null hypothesis. It gets into some pretty complicated logic and ways of thinking, so you don't have to know too much about it, but you do need to know a little bit about what it is. So the value for the power of a hypothesis test depends on the significance level alpha and the value of the population parameter used in the hypothesis test. So where do we actually end up using this? Well, we use it when we're trying to consider sample sizes while we're designing experiments, which we'll get into a little bit later in the course. But beyond that, you don't really need to know much about power of the hypothesis test. Now, we're looking about alpha and beta here. So alpha typically has default values that are selected, and the most common one by far is 5%. So it's a common choice for your significance level alpha. That means that there's a common choice for the power of the hypothesis test, which typically turns out to be 0.80. That's often a very common requirement for a hypothesis test to be effective. Now, there are statisticians who argue that it should be a higher value, such as 0.85 or 0.9, but that discussion is beyond the scope of this class. So, for the power of hypothesis test, just come to understand that it's the probability 1 minus beta of rejecting a false null hypothesis, and it's used when considering sample sizes during the design of an experiment. That's all you really need to know about it. You won't ever have to calculate it or do anything more with it. So when you're designing an experiment, make sure you have a goal to have a power value of at least 0.8 to calculate minimum required sample sizes. And that brings us to the end of this lecture. If you have any questions, you know what you need to do. Otherwise, I will see you in class or the next video. Thanks for watching.